Assalamu alaikum. We know a long, closely wound helical coil is referred as a solenoid. The coil which I hold in my hand has got a small diameter compared to its length. This kind of a coil, whose length is very large compared to its diameter, is usually referred as solenoid. Here I have one more solenoid with me. In this video, we are going to get the expression for self-inductance of a solenoid. For that, I consider one solenoid which has got a n number of turns. And its length is found to be equal to small l. And the area of a cross section of this solenoid is nothing but A, capital A. Now, through one such solenoid, if you pass current I, then it will produce a magnetic field around it. The magnetic field produced by this solenoid appears something like this. This is the magnetic field. Okay, and if you look at the magnetic field lines passing through the axis, it appears to be parallel to each other. And here arrow marks represent the direction of the magnetic field lines. We know when magnetic field lines goes parallel to each other, we call such a magnetic field as uniform magnetic field. Now, in case of a current carrying solenoid, the magnetic field is uniform along its axis. Here, this magnetic field is represented by letter B. And it is mathematically expressed as B equal to mu naught Ni. I named this as equation number 1. This equation number 1 represents the magnetic field produced by a current carrying solenoid. Now, this we have derived long ago. For more information, kindly go through that video. Now, the magnetic field lines are linked with the turns of this solenoid. So, the magnetic flux linked with each turn of this solenoid is represented by letter 5b, and it is found to be equal to B vector dot dA vector. So, to get the magnetic flux, I integrate this. In the next step, this is a constant, so it is taken out. We do not integrate a constant. Only this term is integrated. It is written this way. So, when I integrate dA, I will get A vector. Now, we know very well. When we integrate dx, we get dx. The similar way, when we integrate dA vector, we will get A vector. So, what I will get here, I will get this. D vector dot A vector. Okay, so 5b, which is the magnetic flux linked with the solenoid. Each turn of the solenoid, this is nothing but the dot product of B vector and A vector. Now we know A vector dot the B vector, dot product of two vectors can be represented as AB cos theta. Similar way, here I represent this one as B equals to B A cos theta. Here theta is the angle between magnetic field and the area of cross section of the solenoid. Okay, as you can see, the magnetic field and the area of cross section both lie in the same direction. So the angle between them, both of them lie in the same plane. So the angle between them is nothing but 0. When theta is taken as 0, cos of theta will become cos of 0, and it is nothing but 1. This is what we know. So phi b becomes equal to b a multiplied with 1, and what is this? Phi b is equal to b multiplied with a. I box this for better visibility. Here, this provides us the expression for magnetic flux. I take it as equation number 1. Okay. Now, I will find out the total magnetic flux linked with this solenoid, which consists of n number of turns. So the total magnetic flux linked with the solenoid can be obtained if I multiply this with the total number of turns, which is nothing but n. So equation 1 is multiplied with n phi b gives me total magnetic flux linked with it. When I multiply the left hand side with n, the same thing I have to do with the right hand side as well. So this side also I multiply with the n. Okay, and I had told you earlier here n, capital N is nothing but number of turns per unit length. Here, not capital N, here small n. Small n is nothing but number of turns per unit length. So from this, capital N is equal to n. Okay, this I am going to substitute in the above equation. So what I'll get? I'll get this n phi b becomes equal to n l b a. Okay, this is the total magnetic flux linked with the solenoid. I box this for better visibility. So what is my aim? My aim is to get the self-inductance of this solenoid. And we know the magnetic flux linked with a coil is directly proportional to the current flowing through the coil. So here I take the total magnetic flux linked to the coil, which is nothing but n phi b, and it is found to be equal to, is directly proportional to the current flowing through it, that is I. Now when I remove this proportionality, I have to include a constant along with equal to sign. So n phi b is equal to a constant multiplied with I. I write this as such, and here I replace this constant with the L. So in the place of constant I write L. The L stands for self-inductance or self-induction of a solenoid. Okay. So here I have two equations in which the terms present in the left hand side are same. Box this. I name this one as equation number 2 and this as equation number 3. Now I compare 2 and 3. Comparing equation 2 and 3. So what I'll get? I'll get this. yeah, Li quantum equal to N L B. And here I substitute the value of B, which is given here in equation number 1. Now 1 in equation 4. This is equation 4. If I do so, what I get this Li N L in the place of B. Alright, this mu naught N I E. So the similar terms both sides will cancel. Now what remains here is something like this. N equals to mu naught N multiplied with N gives us N square L and A. This is the final equation which gives us the expression for self-inductance of a long solenoid. It clearly shows that the self-inductance of a current carrying solenoid depends on the geometry, okay, and it also depends on the permeability of medium present within the solenoid. Okay, now suppose this solenoid is placed in a medium whose permeability is mu, then this can be represented as N equals to mu N square L A. Okay, this is a box. Here mu can be written as, we know, relative permeability is the ratio of mu and mu naught. From this, mu is equal to the product of mu naught and mu r. Okay, so in the place of mu I can write this. So this clearly shows that the self-conductance of a solenoid depends on its geometry, that is the length, area of cross section, the number of turns it comprises of. Then it also depends on the medium in which the solenoid is placed. If we vary the medium, then the value of L will vary. I hope the video is useful. If you have any kind of doubt related to the topic, can you put a question in the comment section. Thanks for watching.